D equals V naught T plus 1/2 AT squared. Once you write that equation down, it's pretty easy to convert it to a rotational form. Delta theta equals omega naught T plus 1/2 alpha T squared. Our initial rotational speed is 0, so that part goes out of our equation, and we can solve this thing for time. When you solve what's left for time, you have 2 times delta theta divided by alpha equals T squared. Take the square root of both sides, and you get T. So the time is 2 times delta theta, which is your angular displacement, which is 1 rotation, which is 2 pi radians. So we're going to plug in 2 pi, because we got to plug in the value in radians. Alpha is 2 radians per second squared. This 2 and that 2 cancel. We have the square root of 2 pi, and when you do the math, that ends up at 2.5 seconds. And that's how long it will take this thing to turn through 1 rotation. Now, we're not done. The problem also asks, once you get to 1 rotation, what's your final speed? Okay, if I don't want to use the time, and I want to use the things that were given in the original problem, the final speed is like final velocity. So initial velocity, acceleration, displacement, final velocity, those are all related by that basic kinematic equation. If we convert this to a rotational equation, it looks like that. Our initial angular speed is 0, so we can throw that part away. And our final rotational speed will be the square root of 2 alpha delta theta. So that's the square root of 2 times alpha, 2 radians per second squared, times delta theta, 2 pi. Do the math, and you get an angular velocity of 5 radians per second. Okay? One more problem. Number 6. A ball of radius 5 centimeters rolls from the top to the bottom of a ramp that's 1.25 meters long. At the bottom of the ramp, the ball has a rotational speed of 8 radians per second. If the ball started from rest, determine the angular acceleration and the time to roll down the ramp. Okay, let me get a larger piece of paper to work on. Okay, so let's see what we got here. We got the radius of the ball, 5 centimeters. We have the length of the ramp, 1.25 meters. At the bottom of the ramp, we have a rotational speed of 8 radians per second. That's my final rotational speed. Presumably, we started at rest at the top of the ramp, so omega naught 0. And, it says, if it started from rest, determine the angular acceleration, alpha, and the time to roll down the ramp. Now, your first thought might be, that radius and length of the ramp, I have no clue what to use that for. And so you're sitting here, you're staring at omega naught, which is 0, omega final, which is 8, and you're trying to find alpha and you're trying to find t, and you're not going to go anywhere. Because just like when we first started studying the kinematic equations, to make a kinematic equation work, you need three things. Well, let's think about the other two things they gave you. The ramp is 1.25 meters long, and the ball on it has a radius of 5 centimeters. When the ball rolls down the ramp, it's going to turn through some arc length. Well, guess what? If the ramp is 1.25 meters long, how far do you think the arc length that this ball turns through has to be? If it's not slipping as it comes down the ramp, it's got to turn through 1.25 meters of length. And we have a relationship between the arc length, the radius, and theta. So if we take the arc length, which will have to equal the length of the ramp if we roll down without slipping, and we divide by the radius, we can get theta. So 1.25 meters, the radius is 5 centimeters, or 0.05 meters. Okay. Do the math, and we can find what theta has to equal. And theta is 25 radians. That's the angle the ball had to roll